Okay, in this lesson we're going to continue to look at optimization problems. In the previous lesson we defined a number of things. We have looked at systems of inequalities and how that creates a solution to a problem. And we defined a number of things in part B, which is definitions of constraint, optimization problem, objective function, and feasible region, which is also the solution region. But we haven't gotten practical yet, which may help you understand what the idea is. At some point, if you want to pause this video and try some things on your own, that may be useful for you. So here's the problem that we're going to look at right now. A toy company manufactures two types of toy vehicles, racing cars and sport utility vehicles. So before I move on, part A here just says define the variables and label the axes. I'm going to let S be the number of SUVs and R be the number of race cars. Those are the two things, or the combinations of things that can be made by the toy company. The first bullet here says, because the supply of materials is limited, no more than 40 racing cars and 60 sport utility vehicles can be made each day. So there are actually two constraints as defined in the previous lesson. One constraint is they can't make any more than 40 racing cars. Another constraint is that they can't make any more than 60 sport utility vehicles. Bullet 2 says this, however, the company can make 70 or more vehicles in total each day. So there's another constraint. They can make 70 or more vehicles in total each day. Third bullet, it costs $8 to make a racing car and $12 to make a sport utility vehicle. That's not a constraint, it's just a fact. They're not constrained by the cost here at all. It's just telling you how much that each one costs to make. There are many possible combinations of racing cars and sport utility vehicles that can be made. I actually want to stop there and let's just create or find out all the possible combinations of racing cars and sport utility vehicles that can be made according to these three blue, yellow, and green constraints. I'll show you a few methods for doing each. And we've looked at this in a variety of times, so you might want to pause this at some point in time to try it on your own. So let's look at the first constraint here. No more than 40 racing cars can be made. B says write a system of linear inequalities to represent each constraint. So two ways you can do this as far as graphing your solution region. One would be to come up with your constraint. So no more than 40 racing cars would look like this. Racing cars are always going to be less than or equal to 40. Or, so what I've done here is just because of the numbers that are given to us, I'm going to go up by tens because some of the numbers are like 70 and 40 and 60. So that's what I've decided to go up by on my axes. One way to do it is to use this constraint here, or to ask yourself, either way, what does the boundary R equals 40 looks like? And that would be a horizontal line through the racing car. That's going to be a solid line. That's R equals 40. Okay. Another way you could have come up with that is just to ask yourself, without the inequality, what are 2 points where there's exactly 40 racing cars? Well, here's a point, here's a point, here's a point. So that would be your boundary line for where there's exactly 40 racing cars. Now, if it's no more than 40 racing cars, you could use a test point. Is the point 0 satisfactory? Is 0, in other words, less than 40? And the answer is yes. Or no more than 40 means it's below 40. So the entire region that's below 40 here, which I'll take some time to shade, this would be, any of these points would represent less than 40, less than or equal to 40 racing cars. So that's the first constraint. The second constraint that we're looking at here is that there are no more than 60 sport utility vehicles that can be made in a day. So let's go ahead and look at that one, or maybe while I'm shading this you could pause it and try and represent no more than 60 sport utility vehicles in a day. Okay, so the yellow constraint here, no more than 60 sport utility vehicles in a day, would look like this. Sport utility vehicles have to be less than or equal to 60. Or in other words, your boundary would be where sport utility vehicles are exactly 60. Well, they're exactly 60 here, they're exactly 60 here, or S equals 60 is a vertical line through the S or sport utility axis at 60. So that would look like this. Okay. And which side of that line is less than 60? Well, you could test a point, like the point 0 here. 0 is less than 60, and 80 is more than 60, so it would be the side that's to the left of that line. And I'm going to start shading that in yellow, and what you're going to start noticing is we're starting to find our solution region, because the overlap of yellow and blue makes what you're seeing right now is green. So this green region is representing two things. It's representing where racing cars are less than 40 and sport utility vehicles are less than 60. So we're starting to realize what our solution region or possible combinations that this particular company can make. We have one more constraint, and you might want to start trying it on your own if you'd like to. And what it says is that they can make 70 or more vehicles in total each day. So what did that look like as an inequality, and what will that look like as a graph? So let's go ahead and look at that right now. So the last constraint that I see is the one here in green, which says the company can make 70 or more vehicles in total each day. So it means that when I add the two, so when I take racing cars plus SUVs, sorry, I'll do this in green, racing cars plus SUVs, that's greater than or equal to 70. So your boundary, whether you're using this equation or not, or inequality or not, your boundary is where there's a total of racing cars and SUVs is exactly 70. So if you can come up with 2 points where it's exactly 70, here's one here, where SUVs is 70 and racing cars is 0, and here's another one. Or, if you like to use the equation to get those exact same points, if you substitute r equals 0, you'll get s equals 70, which is this point right here that I just put. And if you substitute s equals 0, you'll get r equals 70, which is right here. So your boundary line is going to be the combinations where they're making exactly 70 cars in a day. So there's your boundary line. And the last thing to ask yourself, you could use a test point or not, is which side of that line would be more than or equal to 70? Well, if I look at this point here, 0, 0, that would be not more than or equal to 70, so it's going to be the opposite side. Or in other words, if I test, if you really wanted to, you could test 0, 0, and you'd find out or ask yourself, is 0 plus 0 greater than 70? And the answer is no. So you'd shade the opposite side. Since I'm out of colors that would combine to make a certain color, I'm just going to use lines like this. You'd shade the opposite side. So the solution region is where the yellow and the blue and the green lines overlap. So you can see here that your solution region is this triangle right there. Okay, so this is your solution region. All right, so part C says this: what do you know about the restrictions on the variables? Well, I can tell you right now that we know that they have to be positive integers. So if you'd like to know the solution region precisely, that's also called whole numbers. You should be crossing out any of the negative quadrants. And you should also be putting integer points inside the solution region, because you can only make or sell whole cars. Part D is already done. We did it as we came up with our constraints. So graph the solution region. We have it here. These are all the possible combinations of cars that can be made. So let's answer the next question. What are 2 possible solutions to the system? I can choose any of these points that are in here. So one possible solution that appears to be 50 sport utility vehicles and 30, so 50 SUVs and 30 race cars, because that meets all the constraints. That's less than or equal to 60 SUVs, that's less than or equal to 40 race cars, and that's more than or equal to 70 in total. Another possibility would be this one here. That would be 60 SUVs and 30 race cars. So there's many combinations within that solution region that would meet that criteria. Part F is kind of the new part. It says what quantity in this situation needs to be minimized or maximized. So this has to do with the objective function. The goal is, once you have the solution region, we want to use that solution region in order to find out some sort of maximum or minimum type of value. And for this particular company, what we're trying to maximize or minimize is the costs. So those are the words we look for. So what are they trying to maximize or minimize? That's going to be the cost. And it says write an equation to represent how the 2 variables relate to this quantity. Well, we know the cost is, I think we read it here, cost is $8 for a racing car and $12 for an SUV. So let me just write out kind of what that is. Cost is $12 for race cars and $8 for an SUV. I think that's correct. $8 for a race car. I'm wrong. Sorry. $8 for a race car and $12 for an SUV. So if you like the actual equation, it would be cost is equal to $8 per race car plus $12 per SUV. We'll investigate what that objective function means a little bit later in a future lesson.